Picture this. Right now, as you listen to these words, invisible cosmic rays from distant galaxies are streaming through your body at nearly the speed of light. Particles that began their journey billions of years ago, when the universe was young and strange, are passing through every cell in your body without you feeling a thing. But these cosmic messengers carry secrets that will fundamentally change how you understand reality itself. We're about to embark on a journey that will reveal the hidden layers of existence surrounding you, from the quantum realm smaller than atoms to cosmic structures larger than anything human minds were meant to comprehend. If you're ready to discover that the universe is far stranger, more interconnected, and more alive than you ever imagined, then prepare yourself for a voyage into the hidden universe that exists all around us right now. Every second of your existence, you're being bombarded by invisible radiation from space. But these aren't just random particles flying through the cosmos. They're time travelers carrying information about events that happened when the universe was barely a fraction of its current age. Cosmic rays are the most energetic particles in the known universe, some carrying more energy than the fastest pitched baseball, concentrated into a space smaller than a proton. When these particles collide with Earth's atmosphere, they create cascades of secondary particles that rain down upon us constantly. Your body is struck by about one cosmic ray particle every few seconds, yet you never feel it. These particles have traveled for millions or billions of years across intergalactic space, surviving journey through magnetic fields, stellar winds, and the vacuum of space itself. But here's what makes cosmic rays truly extraordinary. They originate from some of the most violent and exotic phenomena in the universe. Supernova explosions that can outshine entire galaxies for weeks. Black holes accelerating matter to incredible speeds as they devour everything around them. Neutron stars with magnetic fields a trillion times stronger than Earth's, spinning hundreds of times per second. Active galactic nuclei, where supermassive black holes consume material equivalent to several suns every year, creating jets of particles that stretch across millions of light years. When you're struck by a cosmic ray, you're being touched by the aftermath of cosmic catastrophes that dwarf anything in human experience. Some cosmic rays carry so much energy that scientists still don't understand how nature manages to accelerate particles to such incredible speeds. The most energetic cosmic ray ever detected, recorded in 1991, carried the energy of a baseball thrown at 60 miles per hour, but concentrated into a single atomic nucleus. This particle had traveled across billions of light years of space, maintaining its incredible energy despite countless interactions with magnetic fields and radiation along the way. When it finally struck Earth's atmosphere, it created a cascade of billions of secondary particles spreading across miles of sky. These ultra-high energy cosmic rays pose one of the greatest mysteries in modern astrophysics. The known laws of physics suggest that such energetic particles shouldn't be able to travel very far through space before losing their energy through interactions with background radiation. Yet here they are, striking Earth regularly, apparently originating from sources billions of light years away. This suggests either that our understanding of particle physics is incomplete, or that there are cosmic accelerators out there operating on principles we haven't discovered yet. The sources of these extreme cosmic rays might be exotic objects that challenge our understanding of what's possible in the universe. Perhaps they come from the collision of neutron stars, events so violent they create ripples in space-time itself that we can now detect with gravitational wave observatories. Maybe they originate from the evaporation of primordial black holes, microscopic remnants from the universe's first moments that are finally reaching the end of their incredibly long lives. Or they might come from cosmic strings, hypothetical one-dimensional objects left over from the universe's birth that could stretch across entire galactic superclusters. Some scientists speculate that the highest energy cosmic rays might even originate from outside our observable universe, carrying information about regions of space that light from those areas hasn't had time to reach us yet. If this is true, then cosmic ray astronomy might be our first glimpse into the larger cosmic landscape beyond the horizon of observation, revealing structures and processes operating on scales that dwarf even our immense observable universe. As these cosmic messengers pass through your body, they're also interacting with your DNA, occasionally causing mutations that drive evolution itself. Every life form on Earth has been shaped by cosmic radiation over billions of years. The genetic diversity that allows life to adapt and evolve depends partly on these random cosmic impacts that alter genetic codes in subtle but important ways. You exist partly because cosmic rays from distant galaxies have been gently reshaping life on Earth for eons, creating the genetic variation that natural selection uses to craft new forms of life. But cosmic rays also connect us to the universe in more immediate ways. The carbon atoms in your body were forged in the nuclear furnaces of ancient stars, but the cosmic rays striking you right now carry atoms created in stellar explosions that happened recently in cosmic terms, perhaps just a few million years ago. These particles represent the freshest matter in the universe, atoms that were literally created yesterday on cosmic timescales and have been racing across space to reach you. Advanced civilizations elsewhere in the galaxy might be using cosmic rays as a communication medium. Encoding messages in the patterns of high-energy particles, they accelerate and aim toward promising star systems. The seemingly random distribution of cosmic ray arrivals might contain hidden signals from alien scientists trying to make contact across interstellar distances. Future technology might allow us to decode these cosmic messages and perhaps send replies of our own, establishing a galactic internet based on the most energetic particles in the universe. The cosmic ray bombardment of Earth varies with our planet's journey through the galaxy. As our solar system orbits the Milky Way, we pass through regions of space with different particle densities and magnetic field configurations. These variations might influence Earth's climate over geological timescales, possibly contributing to ice ages and periods of rapid evolutionary change. The cosmic environment around our solar system is constantly changing as we move through the galaxy, exposing Earth to different types and intensities of cosmic radiation. Scientists have discovered that cosmic rays can even influence weather patterns on Earth. When high-energy particles strike the atmosphere, they create charged particles that can seed cloud formation. Variations in cosmic ray intensity might affect cloud cover, which in turn influences global temperature patterns. This connection between cosmic particle physics and terrestrial weather demonstrates how Earth is intimately connected to processes happening throughout the galaxy and beyond. The study of cosmic rays has also revealed that space is not empty. The regions between stars are filled with magnetic fields, gas clouds, and energetic particles, creating a complex and dynamic medium that influences how matter and energy move through the galaxy. Cosmic rays interact with this interstellar medium, creating secondary radiation and exotic particles that don't exist naturally on Earth. The space between stars is alive with activity invisible to our eyes, but detectable through its effects on cosmic ray propagation. Future space missions might use cosmic rays as a navigation system, reading the patterns of particle impacts to determine spacecraft position and orientation even in the depths of interstellar space. The cosmic ray background could serve as a universal reference frame that works anywhere in the galaxy, providing navigation capabilities that don't depend on signals from Earth or other artificial beacons. Now let's journey to the other extreme of scale, into the quantum realm where particles exist in multiple states simultaneously, and reality itself seems to change depending on whether anyone is watching. At the quantum level, The familiar rules of everyday physics break down completely, replaced by strange principles that suggest consciousness might play a fundamental role in determining what becomes real. Quantum mechanics reveals that particles don't have definite properties until they're observed. Before measurement, an electron doesn't have a specific location or speed. Instead, it exists in what physicists call a superposition of all possible locations and speeds simultaneously. This isn't just a limitation of our knowledge about where the particle is. The particle literally exists in multiple states at once until the moment of observation forces it to choose a single definite state. This quantum superposition has been demonstrated in countless experiments, but it remains one of the most puzzling aspects of reality. When scientists fire individual electrons through a double-slit apparatus, each electron somehow goes through both slits simultaneously, interfering with itself to create wave patterns on the detection screen. But if they try to determine which slit each electron actually passes through by placing detectors at the slits, the wave pattern disappears and the electrons behave like normal particles, each going through only one slit. The act of observation literally changes the behavior of quantum particles. This observer effect suggests that consciousness might play a special role in determining physical reality. Some interpretations of quantum mechanics propose that conscious observation causes quantum superpositions to collapse into definite states, making awareness a fundamental feature of the universe rather than something that emerged from complex arrangements of matter. But quantum effects extend far beyond individual particles. Quantum entanglement allows particles to remain mysteriously connected even when separated by vast distances. When two particles become entangled, measuring the properties of one instantly determines the properties of the other, regardless of how far apart they are. Einstein famously called this spooky action at a distance because it seemed to violate his principle that nothing can travel faster than light. Modern experiments have confirmed that quantum entanglement is real and that the correlations between entangled particles are established instantaneously across any distance. Scientists have created entangled particles and separated them by hundreds of miles, then demonstrated that measuring one particle instantly affects the state of its partner. This suggests that at the quantum level, the universe is fundamentally non-local, with distant regions connected in ways that transcend ordinary space and time. Quantum entanglement might explain how biological systems achieve remarkable efficiency in processes like photosynthesis and avian navigation. Living organisms appear to exploit quantum effects that classical physics suggests should be impossible to maintain in warm, noisy biological environments. Plants achieve nearly perfect energy transfer efficiency in photosynthesis through quantum coherence effects that allow energy to explore all possible pathways simultaneously before settling on the most efficient route. Birds might navigate across thousands of miles using quantum entanglement effects in specialized proteins in their eyes that are sensitive to Earth's magnetic field. These quantum biological compasses could provide navigation capabilities far superior to any artificial system, allowing birds to perceive magnetic field directions and intensities with extraordinary precision. The quantum vacuum, the seemingly empty space between particles, turns out to be seething with virtual particle pairs that constantly appear and disappear. These virtual particles aren't just theoretical constructs. They produce measurable effects including the Casimir force, which pushes together metallic plates separated by tiny distances in vacuum. The quantum vacuum also contributes to the magnetic properties of particles and the way light interacts with matter. Some theories suggest that the quantum vacuum might be the source of dark energy, the mysterious force accelerating the expansion of the universe. If virtual particles in empty space contribute a small amount of energy to every region of the universe, this could explain why space itself is expanding at an accelerating rate. The quantum vacuum would be the engine driving cosmic expansion, making every cubic inch of empty space a source of anti-gravitational energy. Quantum field theory reveals that what we think of as particles are actually excitations in underlying quantum fields that permeate all of space. The electron field fills the universe, and what we call an electron is just a localized vibration in this field. Similarly, photons are excitations in the electromagnetic field, and all other particles are manifestations of their corresponding quantum fields. This suggests that the universe is fundamentally made of fields rather than particles, with matter being temporary patterns of field excitation. The quantum nature of reality also implies that the past might not be as fixed as we assume. In quantum mechanics, the properties of particles are undetermined until measurement, and some interpretations suggest that observation in the present can retroactively determine what happened in the past. This backward causation would mean that conscious observers in the present help determine the history that led to their existence, creating self-consistent causal loops that span cosmic time. Quantum computers exploit these strange quantum properties to perform calculations that would be impossible for classical computers. By maintaining quantum superpositions of multiple computational states simultaneously, quantum computers can explore many solution paths in parallel. As quantum computing technology advances, we might develop the ability to simulate quantum processes that govern reality itself, potentially allowing us to model the behavior of quantum fields on cosmic scales. The measurement problem in quantum mechanics suggests that the act of observation is what transforms quantum possibilities into classical realities. But this raises the question of what constitutes an observation. Does it require a conscious observer, or can any interaction with the environment cause quantum collapse? Some theories propose that consciousness is necessary to collapse quantum superpositions, while others suggest that any interaction with other quantum systems is sufficient. If consciousness is necessary for quantum collapse, then the emergence of aware beings in the universe would represent a fundamental phase transition in the nature of reality itself. Before consciousness evolved, the universe would exist in permanent quantum superposition of all possibilities. The first moments of awareness would retroactively select which cosmic history became real, explaining why we observe a universe compatible with the existence of conscious observers. Advanced alien civilizations might have learned to manipulate quantum processes directly, achieving technological capabilities that seem impossible from our current perspective. They could use quantum entanglement for instantaneous communication across galactic distances, quantum superposition for massively parallel computation, and quantum tunneling for transportation through apparently solid barriers. These quantum technologies might allow consciousness to exist in forms we can barely imagine. The quantum realm also suggests that information might be more fundamental than matter and energy. Quantum information theory reveals that the essential properties of quantum systems are informational rather than material. The collapse of quantum superpositions represents information processing events, and quantum entanglement creates correlations that can be understood as information sharing between distant systems. This leads to the possibility that reality itself might be computational, with quantum processes serving as the hardware for a cosmic calculation whose purpose we don't yet understand. The universe might be computing its own evolution through quantum mechanical processes, with each quantum interaction representing a computational step in an unimaginably complex cosmic algorithm. Now let's expand our perspective to consider dark matter and dark energy, the invisible components that comprise most of the universe, yet remain almost completely mysterious to us. Everything you can see, touch, or detect with conventional instruments represents less than 5% of what actually exists. The remaining 95% consists of dark matter and dark energy, substances that interact with ordinary matter so weakly that we can only detect them through their gravitational effects. Dark matter was first discovered when astronomers noticed that galaxies rotate faster than they should based on the amount of visible matter they contain. The outer regions of spiral galaxies orbit the galactic center at speeds that should fling them into space if gravity from visible stars and gas was the only force holding them together. This suggests that galaxies are embedded in vast halos of invisible matter that provides the additional gravitational pull needed to keep them stable. Computer simulations of cosmic evolution show that dark matter is essential for forming the large-scale structure of the universe. Without dark matter, ordinary matter would never have been able to clump together strongly enough to form galaxies and stars. The cosmic web of filaments and voids that characterizes the universe on the largest scales is actually a scaffold of dark matter upon which ordinary matter accumulated over billions of years. The nature of dark matter remains one of the greatest mysteries in modern physics. It could consist of exotic particles that interact only through gravity and possibly the weak nuclear force, making them nearly impossible to detect directly. These particles might be left over from the universe's earliest moments, created in the extreme conditions just after the Big Bang, when the laws of physics may have allowed for types of matter that can't be created under current conditions. Alternative theories suggest that dark matter might not be particles at all, but rather a sign that our understanding of gravity is incomplete. Modified theories of gravity propose that gravitational force behaves differently on galactic and cosmic scales than it does in the solar system, eliminating the need for exotic dark matter particles. However, most evidence favors the particle interpretation, and scientists around the world are building increasingly sensitive detectors to search for dark matter interactions. Dark matter might exist in parallel structures that mirror but don't interact with ordinary matter. There could be dark stars made of dark matter, dark planets orbiting them, and perhaps even dark life forms that have evolved in this invisible cosmic shadow. These dark structures would be completely undetectable except for their gravitational influence on ordinary matter, creating a hidden universe that occupies the same space as our visible cosmos. Some theories propose that dark matter particles could occasionally interact with each other, creating dark photons and other dark radiation. This would allow dark matter structures to cool and condense, just like ordinary matter, potentially forming complex dark matter objects, including dark equivalents of stars and planets. The dark matter halo surrounding our galaxy might contain intricate structures invisible to all our instruments. Dark energy presents an even greater mystery. Discovered through observations of distant supernova in the 1990s, dark energy appears to be accelerating the expansion of the universe. Instead of gravity gradually slowing cosmic expansion as expected, space itself is expanding faster and faster, driven by some form of energy that fills every cubic inch of vacuum with anti-gravitational pressure. The amount of dark energy needed to explain cosmic acceleration corresponds to an incredibly tiny energy density, about 1 atom's worth of mass energy per cubic meter of space. Yet this minuscule energy density dominates the entire universe because it's present everywhere. Every region of empty space contributes to cosmic expansion, making dark energy the most influential component in determining the universe's ultimate fate. If dark energy continues to accelerate cosmic expansion, the universe faces a lonely future called the Big Rip. As space expands faster and faster, it will eventually overcome all other forces, first separating galaxy clusters, then galaxies themselves, then solar systems, and finally tearing apart atoms themselves as the fabric of space-time expands faster than particles can hold together. The universe would end in about 20 billion years when expansion becomes infinite and all structure is destroyed. But dark energy might not remain constant over cosmic time. Its strength could change as the universe evolves, potentially increasing to cause the Big Rip, decreasing to allow cosmic expansion to reverse into a big crunch, or oscillating to create cycles of expansion and contraction. The true nature of dark energy will determine whether the universe ends in ice, fire, or something completely unexpected. Some theories propose that dark energy is the energy of empty space itself, arising from quantum fluctuations in the vacuum. However, quantum field theory predicts that vacuum energy should be enormous, about 120 orders of magnitude larger than observed. This cosmological constant problem represents the worst disagreement between theory and observation in all of science, suggesting that our understanding of either quantum mechanics or gravity is fundamentally flawed. Alternative explanations for dark energy include the possibility that we're observing the effects of extra dimensions. If our three-dimensional space is embedded in a higher dimensional reality, then gravity might leak into these extra dimensions on cosmic scales, creating apparent acceleration in our dimensional slice. This would mean that dark energy isn't actually energy at all, but rather a geometric effect arising from the true multidimensional structure of space-time. Dark energy might also be dynamic, changing over time in response to the evolution of matter and structure in the universe. Scalar fields similar to the Higgs field could permeate space and drive cosmic acceleration, with their properties evolving as the universe expands and cools. These quintessence fields could interact with dark matter and ordinary matter in subtle ways, creating complex feedback loops that determine cosmic evolution. The combination of dark matter and dark energy might create phase transitions in cosmic evolution that we haven't yet recognized. Just as water undergoes sudden changes from liquid to gas when heated, the cosmic mixture of matter, and dark energy might undergo sudden transitions that dramatically alter the expansion rate and structure formation processes. We might be living during one such transition period, explaining why dark energy appeared to dominate cosmic evolution relatively recently in cosmic history. Advanced civilizations might learn to manipulate dark matter and dark energy directly, achieving technological capabilities that transcend anything possible with ordinary matter alone. Dark matter manipulation could allow for gravitational engineering on galactic scales, while dark energy control could enable faster than light travel by locally manipulating the expansion rate of space itself. The detection of dark matter and dark energy interactions might reveal that these invisible components are part of a much richer dark sector of physics. There could be entire periodic tables of dark elements, dark chemistry creating dark molecules, and dark electromagnetic forces creating dark light invisible to our instruments. The dark universe might be as complex and varied as the ordinary universe we can observe. Future astronomical surveys might detect subtle signatures of dark matter and dark energy interactions, revealing the hidden dynamics that govern cosmic evolution. Gravitational wave detectors might observe collisions between dark matter objects, while next-generation telescopes might map the distribution of dark energy through its effects on light from distant galaxies. The study of cosmic structure reveals another layer of hidden complexity in the universe. On the largest scales, matter is organized into a cosmic web of filaments and voids that spans billions of light years. This structure emerged from tiny quantum fluctuations in the early universe that grew over billions of years through gravitational amplification, creating the scaffolding upon which galaxies formed. The cosmic web resembles a three-dimensional spider web, with galaxies strung along filaments of dark matter, separated by vast voids containing almost no matter at all. These voids are not truly empty, but represent regions where dark matter and ordinary matter are extremely sparse compared to the dense filaments where galaxies cluster. The largest voids span hundreds of, millions of light years, representing volumes of space so vast that they contain fewer galaxies than our local neighborhood. Computer simulations show that this cosmic web structure is highly dynamic, with filaments growing and merging over time as gravity pulls matter into increasingly dense concentrations. Galaxies flow along these filaments like beads on cosmic strings, occasionally colliding and merging when filaments intersect. Our own Milky Way galaxy is part of the Local Group, which is itself embedded in the larger Virgo supercluster, a structure containing thousands of galaxies spread across more than 100 million light-years. But even superclusters are just components in larger structures. The observable universe contains millions of superclusters connected by filaments in a hierarchy of structure that extends to the largest scales we can observe. The cosmic web continues beyond our observational horizon, suggesting that the universe is structured on scales much larger than we can directly study. The formation of cosmic structure depends critically on the properties of dark matter and dark energy. Different types of dark matter would produce different patterns of structure formation, while variations in dark energy could dramatically alter the timeline of cosmic evolution. The cosmic web we observe provides crucial clues about the nature of these mysterious components that dominate the universe. Within this cosmic web, galaxies themselves hide numerous mysteries. Most galaxies harbour supermassive black holes at their centres, objects millions or billions of times more massive than our Sun, compressed into regions smaller than our solar system. These black holes appear to regulate star formation throughout their host galaxies through feedback processes that eject material and energy far beyond the galaxy's boundaries. The relationship between black holes and galaxies suggests that these two components co-evolved over cosmic time, with black hole growth influencing galaxy development and vice versa. This symbiotic relationship might explain why galaxies have the specific properties we observe, including their sizes, shapes, and star formation rates. The universe might have naturally selected for galaxy black hole combinations that achieve stable configurations capable of producing complex chemistry and potentially life. Some galaxies contain multiple supermassive black holes orbiting each other, remnants of galaxy mergers that brought separate black holes together. These binary black hole systems will eventually spiral together and merge, producing gravitational waves detectable across cosmic distances. The merger process releases enormous amounts of energy, potentially ejecting the resulting black hole from its host galaxy entirely. Active galactic nuclei, powered by matter falling into supermassive black holes, can outshine all the stars in their host galaxies combined. These quasars and blazars create jets of particles that extend across millions of light-years, influencing star formation and galaxy evolution far beyond the immediate vicinity of the black hole. The energy output from active galactic nuclei can exceed the luminosity of 1 trillion suns, making them visible across most of the observable universe. The study of galaxy formation reveals that the first galaxies formed when the universe was less than 1 billion years old, much earlier than previously expected. These primordial galaxies were smaller and more chaotic than modern galaxies, with intense star formation rates that rapidly converted gas into stars. The chemical elements heavier than hydrogen and helium were first created in the nuclear furnaces of stars in these early galaxies, beginning the process of chemical evolution that eventually allowed rocky planets and life to form. Galaxy interactions and mergers play crucial roles in cosmic evolution. When galaxies collide, their gravitational interactions can trigger bursts of star formation, feed supermassive black holes, and dramatically alter galaxy morphology. Our Milky Way is currently approaching a collision with the Andromeda galaxy that will occur in about 4 billion years, creating a new elliptical galaxy that astronomers have dubbed Milkomeda. The space between galaxies is not empty, but contains a warm, hot intergalactic medium composed of ionized gas heated to millions of degrees. This diffuse medium contains more ordinary matter than all the stars in all the galaxies combined, yet it's so sparse that it's nearly impossible to detect directly. The intergalactic medium serves as a reservoir of material that galaxies can accrete over time, fueling continued star formation and growth. Cosmic rays from distant galaxies travel through this intergalactic medium, carrying information about cosmic ray acceleration processes throughout the universe. The highest energy cosmic rays might originate from active galactic nuclei, billions of light years away, making them messengers from some of the most extreme environments in the cosmos. Future cosmic ray observatories might detect patterns in these particles that reveal details about galaxy formation and evolution across cosmic time. The magnetic fields threading through galaxies and the intergalactic medium play important roles in cosmic evolution that we're only beginning to understand. These magnetic fields can influence star formation, accelerate cosmic rays, and affect the behavior of ionized gas throughout the universe. The origin of cosmic magnetic fields remains mysterious, but they appear to be fundamental components of cosmic structure formation. Let's now explore the possibility that we're not alone in this vast cosmos. The search for extraterrestrial life has evolved from science fiction speculation to rigorous scientific investigation, driven by discoveries that suggest life might be far more common in the universe than previously imagined. The detection of thousands of exoplanets orbiting other stars has revolutionized our understanding of planetary systems. We now know that planets are incredibly common throughout the galaxy, with most stars hosting planetary systems of some kind. Many of these planets orbit within their star's habitable zone, the range of distances where liquid water could exist on planetary surfaces. But habitability depends on much more than just distance from a star. Planetary atmospheres, magnetic fields, geological activity, and orbital characteristics all influence whether a world can support life as we know it. Some planets might be habitable despite being outside the traditional habitable zone if they have thick atmospheres that create greenhouse warming, or if tidal heating from gravitational interactions keeps subsurface oceans liquid. The discovery of extremophile organisms on Earth has expanded our concept of habitability dramatically. Life exists in environments previously thought to be completely sterile, including boiling hot springs, highly acidic pools, extremely salty lakes, and even in rocks miles below Earth's surface. These extremophiles demonstrate that life is incredibly adaptable and might exist in environments throughout the solar system and beyond that we never considered potentially habitable. Jupiter's moon Europa and Saturn's moon Enceladus harbour subsurface oceans that contain more water than all Earth's oceans combined. These hidden seas are kept liquid by tidal heating from their host planet's gravity, and they might provide stable environments for life to evolve over billions of years. Future missions to these moons might discover entire ecosystems existing in the darkness beneath their icy shells, sustained by chemical energy rather than sunlight. Mars shows evidence of ancient river valleys, lake beds, and possibly even oceans, suggesting that the red planet was once much warmer and wetter than it is today. Traces of organic molecules in Martian rocks hint that the planet might have supported life in the past, and possibly still does in subsurface environments protected from the harsh surface conditions. The discovery of liquid water beneath Mars's polar ice caps adds another potential habitat for current Martian life. The detection of phosphine in Venus's atmosphere caused excitement because this molecule is produced by life on Earth and rapidly destroyed by chemical processes, suggesting that something might be continuously replenishing it in Venus's atmosphere. While follow-up observations have cast doubt on the initial phosphine detection, the possibility of aerial life in Venus's upper atmosphere remains intriguing. The acid clouds of Venus might provide a niche for extremophile organisms adapted to highly acidic conditions. Interstellar space itself might harbour life forms adapted to the cosmic environment. Panspermia theories suggest that life might travel between star systems as dormant spores protected by cosmic dust grains or small asteroids. Some microorganisms can survive for extended periods in the vacuum of space, protected from radiation by entering cryptobiotic states where all metabolic activity ceases until conditions improve. The search for intelligent life focuses on detecting technological signatures that would indicate the presence of advanced civilizations. Radio telescopes scan the skies for artificial signals, while optical telescopes look for laser pulses that might represent attempts at interstellar communication. The absence of obvious alien signals might indicate that intelligent civilizations are rare, short-lived, or using communication methods we haven't considered. Advanced civilizations might build megastructures around their stars to capture energy for their growing technological needs. Dyson spheres, swarms of solar collectors surrounding entire stars, would appear as stars that emit primarily in infrared radiation rather than visible light. While no confirmed Dyson sphere candidates have been found, several stars show unusual dimming patterns that could potentially indicate artificial structures. The Fermi Paradox highlights the apparent contradiction between the high probability of extraterrestrial civilizations and the lack of evidence for their existence. Various solutions have been proposed, including the possibility that intelligent life is extremely rare, that civilizations tend to destroy themselves, or that aliens are deliberately avoiding contact with less developed species like humanity. Breakthrough Listen and other SETI projects are expanding their search strategies to look for a wider variety of potential signals. Instead of just radio waves, researchers are now looking for optical pulses, infrared emissions, and even gravitational wave signatures that might indicate alien technology. Machine learning algorithms help analyze vast amounts of data to identify patterns that human observers might miss. The discovery of interstellar objects like Oumuamua and Borisov passing through our solar system raises the possibility that some of these visitors might be artificial probes rather than natural asteroids or comets. Oumuamua's unusual elongated shape and acceleration away from the Sun sparked speculation about its artificial nature, though natural explanations are considered more likely by most scientists. If we do detect signs of extraterrestrial life, the implications would be profound for human civilization. The discovery of even microbial life elsewhere would suggest that life is a common feature of the universe, while contact with intelligent aliens would revolutionize our understanding of our place in the cosmos. Protocols exist for how humanity should respond to confirmed alien contact, but the actual discovery would likely unfold in unpredictable ways. Advanced alien civilizations might have already visited Earth in the past, leaving traces in the geological record or even in biological systems. Some scientists have proposed that life on Earth might have been seeded by aliens billions of years ago, a directed panspermia hypothesis that could explain some puzzling aspects of terrestrial biochemistry. However, such claims remain highly speculative and lack convincing evidence. The possibility of encountering alien life raises important questions about how we should interact with non-human intelligence. Should we try to make contact, or would this be too risky? How would we communicate with beings whose evolution followed completely different pathways? These questions become increasingly relevant as our detection capabilities improve and the probability of discovery increases. Future space telescopes will be capable of analyzing the atmospheres of Earth like exoplanets, searching for biosignatures like oxygen, water vapor, and other molecules associated with life. The James Webb Space Telescope and planned missions like the Habitable Exoplanet Observatory might detect signs of life on distant worlds within the next few decades, potentially answering one of the most fundamental questions about our universe. the search for life also drives the exploration of our own solar system. Missions to Europa, Enceladus, Titan, and Mars are specifically designed to look for signs of past or present life. The discovery of life anywhere in our solar system would suggest that life is common throughout the universe, since the processes that created life here would likely operate elsewhere as well. As we expand our search for life, we must also consider the possibility that alien intelligence might be so different from human intelligence that we wouldn't recognize it as conscious. Silicon-based life, quantum-coherent organisms, or even digital intelligences existing in vast computer networks might think and perceive reality in ways so alien that communication would be nearly impossible. Now let's journey to the very edge of space and time to explore black holes, objects so extreme that they challenge our understanding of reality itself. Black holes represent the ultimate victory of gravity over all other forces, creating regions of space-time where the familiar laws of physics break down and entirely new phenomena emerge. When a massive star exhausts its nuclear fuel and can no longer generate enough pressure to support itself against its own gravity, it undergoes catastrophic collapse. In less than a second, the star's core compresses from the size of Earth to a point of infinite density called a singularity, while the outer layers are blown away in a spectacular supernova explosion. The resulting black hole contains more mass than our Sun, compressed into a region smaller than a city, creating gravitational fields so intense that not even light can escape. The boundary surrounding a black hole, called the event horizon, represents the point of no return. Any object that crosses the event horizon is doomed to fall into the singularity, unable to send any information back to the outside universe. From the perspective of an outside observer, objects falling into black holes appear to slow down and freeze at the event horizon, their images growing redder and dimmer until they fade from view. But from the perspective of the falling object, the journey continues normally until they reach the singularity and are destroyed by infinite tidal forces. This difference in perspectives highlights one of the strangest features of black holes. Time itself behaves differently in strong gravitational fields, running slower near massive objects. At the event horizon of a black hole, time dilation becomes so extreme that an outside observer would see time stop completely for anything crossing the boundary. This effect demonstrates that space and time are not separate, absolute quantities, but form a unified space-time fabric that can be warped and distorted by matter and energy. The singularity at the center of a black hole represents a breakdown of our current understanding of physics. General relativity predicts that matter at the singularity reaches infinite density and zero volume, conditions that make no physical sense. Most physicists believe that. New physics, possibly involving quantum gravity effects, must take over before infinite conditions are reached, but we don't yet know what happens inside black holes. Some theories suggest that black holes might be wormholes connecting different regions of space-time or even different universes entirely. The matter falling into a black hole might not be destroyed, but instead transported to another location in space and time, possibly emerging from white holes that spew matter and energy outward instead of consuming it. While white holes have never been observed, they represent valid solutions to Einstein's equations and could exist in remote regions of space or time. Rotating black holes, called Kerr black holes, exhibit even stranger properties than their non-rotating counterparts. The rotation drags space-time itself around the black hole, creating a region called the ergosphere, where nothing can remain stationary relative to distant stars. Objects in the ergosphere are forced to rotate along with the black hole's spin, and theoretical calculations suggest that it might be possible to extract energy from rotating black holes through the Penrose process. The most massive black holes in the universe, Supermassive black holes containing millions or billions of solar masses reside at the centers of galaxies and play crucial roles in cosmic evolution. These giants grow by consuming gas, stars, and other black holes, occasionally producing enormous jets of particles that extend across millions of light years. The relationship between supermassive black holes and their host galaxies suggests that these objects co-evolved over cosmic time. When supermassive black holes consume matter, they can become the most luminous objects in the universe. Active galactic nuclei powered by black hole accretion can outshine all the stars in their host galaxies, making them visible across billions of light years. Some quasars produce jets of particles moving at nearly the speed of light, creating beacons that can be detected across most of the observable universe. The recent detection of gravitational waves has opened a new window for studying black holes. When two black holes orbit each other and eventually merge, they create ripples in space-time itself that propagate outward at light speed. These gravitational waves carry information about the merging black holes, including their masses, spins, and the dynamics of their final moments before collision. The LIGO and Virgo detectors have revolutionized our understanding of black holes by allowing us to observe them directly through their gravitational wave signatures. We've discovered that black hole mergers are surprisingly common, occurring somewhere in the observable universe about once every few minutes. Each merger releases more energy in gravitational waves than all the stars in the observable universe emit in light, yet this energy is spread so thinly across space that it barely disturbs the most sensitive instruments ever built. Some black hole mergers have produced unexpected results, including black holes with masses in ranges that stellar evolution theory suggested should be impossible. These intermediate mass black holes might form through different processes than stellar collapse, perhaps through the direct collapse of primordial gas clouds in the early universe, or through the merger of smaller black holes in dense stellar clusters. Black holes might not be the ultimate destroyers we once thought. Stephen Hawking discovered that black holes actually emit radiation due to quantum effects near the event horizon. Virtual particle pairs that appear near the horizon can be separated by the black hole's gravity, with one particle escaping as Hawking radiation, while its partner falls into the black hole. This process causes black holes to slowly evaporate over incredibly long timescales. The temperature of Hawking radiation is inversely related to the black hole's mass, meaning that smaller black holes are actually hotter than larger ones. Stellar mass black holes have temperatures far below that of the cosmic microwave background radiation, so they're currently growing by absorbing background radiation faster than they evaporate. But as the universe expands and cools, eventually even the most massive black holes will begin to shrink through Hawking radiation. The evaporation of black holes through Hawking radiation creates one of the most profound paradoxes in modern physics. Information that falls into a black hole appears to be destroyed when the black hole evaporates, violating the fundamental principle that information cannot be destroyed in quantum mechanics. Various solutions have been proposed, including the possibility that information is somehow encoded on the black hole's surface, or that black holes don't completely evaporate, but leave behind information-rich remnants. Some theoretical physicists propose that black holes might be holographic objects with all the information about their three-dimensional interior encoded on their two-dimensional surfaces. This holographic principle suggests that our entire universe might work the same way, with all the information in any volume of space encoded on its boundary surface. If this is correct, then our three-dimensional reality might be a holographic projection from information stored on a distant cosmic boundary. The interiors of black holes might contain entirely different universes, pocket cosmoses that exist inside the event horizon, with their own space, time, and physical laws. Every black hole in our universe might be a portal to a universe where space and time began with that black hole's formation. This suggests that the Big Bang that created our universe might have been the formation of a black hole in some parent universe, making our cosmos the interior of a black hole. Advanced civilizations might find ways to harness the incredible energy output of black holes. The accretion disks around rotating black holes convert matter to energy with efficiencies far greater than nuclear fusion, making them potentially ideal power sources for highly advanced technologies. Civilizations that learn to control black hole accretion might gain access to energy sources that could power their activities for billions of years. Some theories suggest that information processing might continue inside black holes, potentially allowing consciousness to survive the journey past the event horizon. If the interior of a black hole contains expanding space similar to our own universe, then falling observers might experience vast amounts of time and space opening up before them as they approach the central singularity. This could provide environments where consciousness could exist for subjectively infinite durations. The study of black holes has led to insights about the fundamental nature of space-time itself. The mathematics describing black holes reveals connections between gravity, thermodynamics, and information theory that suggest deep principles governing the structure of reality. Black holes have entropy proportional to their surface area rather than their volume, hinting that information might be more fundamental than the space that contains it. Primordial black holes, formed from extremely dense regions in the early universe, might make up some or all of the dark matter that dominates cosmic structure formation. These ancient black holes could have masses ranging from microscopic to stellar scales, and they would be virtually impossible to detect directly unless they're actively consuming matter. Some primordial black holes might be evaporating through Hawking radiation right now, contributing to the cosmic ray background and other high-energy phenomena. The possibility of microscopic black holes being created in high-energy particle collisions initially caused concern about the safety of particle accelerators like the Large Hadron Collider. However, calculations show that such tiny black holes would evaporate almost instantaneously through Hawking radiation, releasing their energy harmlessly. The creation and observation of microscopic black holes might provide direct tests of quantum gravity theories and insights into the fundamental structure of space-time. Future observations of black holes might reveal signatures of quantum gravity effects near the event horizon, where the curvature of space-time becomes so extreme that quantum mechanical properties of gravity become important. These observations could help us understand how general relativity and quantum mechanics merge into a unified theory of quantum gravity, potentially solving some of the deepest mysteries in theoretical physics. Let's now journey to the very beginning and end of time to explore the ultimate questions about cosmic origins and destiny. The story of our universe spans nearly 14 billion years, from the moment when space and time began in the Big Bang to a future so distant that all stars will have died and even black holes will have evaporated away. The cosmic microwave background radiation provides our oldest observable evidence about the universe's history, showing us how space looked when it first became transparent about 380,000 years after the Big Bang. Before this time, the universe was filled with a hot plasma that scattered light, making it opaque like the interior of a star. When the universe cooled enough for electrons to combine with protons and form neutral hydrogen atoms, space suddenly became transparent and light could travel freely across cosmic distances. This moment of cosmic dawn, called recombination, released the photons we now observe as the cosmic microwave background. These ancient photons have been traveling through space for over 13 billion years, stretched by cosmic expansion from visible light to microwave radiation. The tiny temperature variations in this background radiation reveal the seeds of structure that would eventually grow into galaxies and galaxy clusters through gravitational amplification. the cosmic microwave background is remarkably uniform across the sky, with temperature variations of only about 1 part in 100,000. This extraordinary uniformity suggests that widely separated regions of space were once in causal contact, even though they're now so far apart that light hasn't had time to travel between them since the Big Bang. This horizon problem led to the development of cosmic inflation theory. Inflation proposes that the universe underwent a period of exponential expansion during its first fraction of a second, stretching tiny quantum fluctuations to cosmic scales, and explaining both the uniformity of the cosmic microwave background and the seeds of structure formation. During inflation, space expanded faster than light, which is allowed because space itself can expand at any rate without violating relativity's prohibition on faster-than-light travel through space. The inflationary epoch might have created not just our observable universe, but an infinite number of separate cosmic regions, each with potentially different physical properties. This eternal inflation scenario suggests that our Big Bang was just one bubble in an infinite cosmic foam, with new bubbles constantly forming through quantum fluctuations in the inflating space between existing universes. If eternal inflation is correct, then the question of what existed before our Big Bang has a clear answer. Other universes were forming and evolving in the larger inflating space that gave birth to our cosmic bubble. The multiverse of eternal inflation would contain every possible combination of physical laws and initial conditions, making our apparently fine-tuned universe just one member of an infinite ensemble where every possibility is realized somewhere. But inflation itself must have had a beginning, pushing the question of ultimate origins to an even earlier era. The singularity theorems of general relativity suggest that if the universe is expanding and contains matter, then tracing backwards in time must lead to a moment when space and time themselves began. This Big Bang singularity represents the limit of what physics can currently describe, a moment of infinite density and temperature where known laws break down. Quantum gravity theories attempt to describe what happens at the Planck scale, the incredibly tiny size and timescales where quantum effects become important for gravity itself. At the Planck time, about 10 to the minus 43 seconds after the Big Bang, quantum fluctuations in space-time itself become significant, and our classical understanding of space and time as smooth continuous quantities breaks down. Loop quantum gravity suggests that space and time are not infinitely divisible, but have discrete smallest units, like pixels in a cosmic computer screen. In this theory, the Big Bang singularity is replaced by a quantum bounce, where a previous universe collapsed to the Planck scale before rebounding into our current expansion phase. This would make our universe cyclic, with infinite sequences of expansion, collapse, and rebirth. String theory offers different perspectives on cosmic origins, suggesting that our universe might be a membrane in higher dimensional space that collided with another membrane, releasing the energy we observe as the Big Bang. This ekpyrotic scenario eliminates the need for inflation by proposing that the collision naturally produced the uniform conditions we observe in the cosmic microwave background. Some theories propose that time itself might have emerged gradually rather than beginning abruptly at a singularity. In these models, the concept of before the Big Bang becomes meaningless, not because time had a definite beginning, but because time itself evolved from a more fundamental atemporal reality where causation worked differently than in our current universe. The anthropic principle suggests that we observe physical constants compatible with our existence, not because they were designed or selected, but because we couldn't exist in universes with different constants. If infinitely many universes exist with different physical properties, then observers will naturally find themselves in universes capable of supporting observation, regardless of how improbable such universes might be. Looking toward the future, the fate of our universe depends critically on the nature of dark energy. If dark energy remains constant, the universe will continue expanding and cooling until it reaches a state of maximum entropy called heat death. All stars will exhaust their fuel and die, leaving behind white dwarfs, neutron stars, and black holes drifting in an increasingly cold and empty cosmos. Even black holes won't last forever. Through Hawking radiation, they will slowly evaporate over timescales so long that the current age of the universe is just an instant by comparison. The most massive black holes will take about 10 to the power of 100 years to evaporate completely, long after all normal matter has decayed into elementary particles. The final era of the universe might be dominated by photons, neutrinos, and electrons drifting through an ever-expanding space approaching absolute zero temperature. But if dark energy grows stronger over time, the universe might end much more dramatically in a big rip. Accelerating expansion would eventually overcome all other forces, first separating galaxy clusters, then galaxies, then solar systems, and finally tearing apart atoms and subatomic particles themselves. Space would expand so rapidly that the fundamental forces couldn't hold matter together, ending the universe in about 22 billion years when expansion becomes infinite. Alternatively, if dark energy decreases or becomes repulsive, cosmic expansion could slow, stop, and reverse into a big crunch. Gravity would win the ultimate battle, pulling all matter and energy back together in a collapse that mirrors the Big Bang in reverse. The final moments would see temperatures and densities rising toward infinity as all structure is destroyed in the cosmic compression. Some cyclic universe models suggest that the Big Crunch could trigger a new Big Bang, creating an endless sequence of cosmic death and rebirth. Each cycle might last trillions of years, with slight variations accumulating over cosmic generations to produce different physical properties in successive universes. Information from previous cycles might survive the transition, allowing the universe to evolve and become more complex over multiple generations. Advanced civilizations far in the future might develop technologies that allow them to influence cosmic evolution directly. They could potentially manipulate dark energy, create artificial universe bubbles, or transfer their consciousness to more stable physical substrates that could survive cosmic catastrophes. The ultimate fate of the universe might depend on the choices made by intelligent beings rather than just the laws of physics. The deep connection between quantum mechanics and cosmology suggests that consciousness itself might play a role in determining cosmic evolution. If quantum measurement effects require conscious observers, then the survival and proliferation of consciousness might be necessary for the universe to continue evolving rather than remaining in quantum superposition of all possibilities. As we conclude our journey through the hidden universe, we find ourselves confronting the deepest mysteries of existence itself. We've discovered that reality is far stranger than our everyday experience suggests, filled with invisible particles and forces, quantum uncertainties and cosmic structures that dwarf human comprehension. We've seen that our universe might be just one bubble in an infinite multiverse, that time itself might be an emergent property rather than a fundamental aspect of reality, and that consciousness might play a crucial role in determining what becomes real. The hidden universe surrounding us operates according to principles that challenge our most basic assumptions about the nature of existence. Particles can be in multiple places simultaneously until observed. Empty space seethes with virtual particles and quantum fields, and the vast majority of the universe consists of dark matter and dark energy whose nature remains almost completely mysterious. Yet these discoveries also reveal deep connections between seemingly disparate phenomena. The same quantum mechanics that governs subatomic particles might determine the large-scale structure of the universe. The black holes that represent gravity's ultimate victory might be holographic entities that store information about their three-dimensional interiors on two-dimensional surfaces. The cosmic web of dark matter that provides scaffolding for galaxy formation might be threaded with magnetic fields and energetic particles that connect distant regions of space. Perhaps most remarkably, we've found that we are not separate from these cosmic processes but intimately connected to them. The atoms in our bodies were forged in stellar furnaces billions of years ago. Cosmic rays from distant galaxies pass through us constantly, occasionally causing genetic mutations that drive evolution. The quantum vacuum that fills space might be the source of consciousness itself, and our observations might play a fundamental role in collapsing quantum possibilities into experienced realities. The search for extraterrestrial life reminds us that Earth might not be unique, and that consciousness might emerge wherever conditions permit complex chemistry and information processing. The discovery of life elsewhere would fundamentally change our perspective on our place in the cosmos, while the continued absence of detectable alien civilizations raises profound questions about the future of intelligence in the universe. As we look toward the future, we face both extraordinary opportunities and ultimate challenges. Advancing technology might allow us to detect dark matter directly, communicate with extraterrestrial civilizations, manipulate quantum processes on macroscopic scales, and even influence cosmic evolution itself. Yet we also confront the possibility that the universe is destined for heat death, that consciousness might be a rare and temporary phenomenon, and that the physical laws themselves might be contingent rather than necessary. The hidden universe reveals that reality extends far beyond what we can directly perceive, encompassing scales from the quantum foam to cosmic structures billions of light years across. Our journey has shown that the cosmos is not a static backdrop for human existence, but a dynamic, evolving system where matter, energy, space, and time are continuously being created, transformed, and potentially destroyed. Understanding our place in this vast and largely invisible cosmos is perhaps humanity's greatest intellectual challenge. We are conscious beings who have emerged from cosmic evolution, capable of contemplating the universe that created us. Whether consciousness is a fundamental feature of reality or an emergent property of complex information processing, it represents something genuinely new in cosmic history, the universe developing the ability to observe and understand itself. The hidden universe that surrounds and permeates every aspect of our existence continues to reveal new layers of complexity and beauty. From quantum fields fluctuating in empty space to dark energy accelerating cosmic expansion, from primordial black holes that might comprise dark matter to gravitational waves that carry information across cosmic distances, the invisible universe is as rich and varied as anything we can directly observe. Our exploration of these hidden realms has shown that the fundamental nature of reality remains deeply mysterious. We don't know why the universe exists, why it has the particular properties we observe, or whether our existence represents an inevitable outcome of cosmic evolution or an incredibly unlikely accident. The anthropic principle suggests that we observe a universe compatible with our existence because we couldn't exist otherwise, but this doesn't explain why any universe exists at all. The possibility that our universe is just one member of an infinite multiverse pushes these questions to even greater scales. If every possible universe exists somewhere in the multiverse, then our apparently fine-tuned cosmos becomes statistically inevitable rather than mysteriously special. Yet this explanation requires accepting the existence of unobservable realities that might forever remain beyond scientific investigation. As we continue to probe the hidden universe with increasingly sophisticated instruments and theories, we might discover that reality is even stranger than our current models suggest. Future observations might reveal new forms of matter and energy, additional spatial dimensions, or connections between quantum mechanics and gravity that fundamentally change our understanding of existence itself. The journey into the hidden universe ultimately returns us to ourselves, conscious beings wondering about the nature of consciousness, observers trying to understand observation, products of cosmic evolution investigating the processes that created us. In seeking to comprehend the hidden universe, we participate in the cosmos coming to know itself through the awareness that emerged from its own evolutionary processes. Whether we are alone in this vast cosmic theatre or part of a community of conscious beings scattered throughout space and time, our quest to understand the hidden universe represents one of the most remarkable developments in cosmic history. From quantum particles to cosmic structures, from the Big Bang to the ultimate fate of everything, the hidden universe continues to surprise, challenge, and inspire us as we work to comprehend our place in the magnificent cosmic story that is still being written around us and through us every moment of our existence.